And welcome to our official start of data structures for today. So I've got a few announcements for us, so I'll share my screen and we'll start off with that. So the first announcement is related to our announcement last time about the upcoming course offerings for the upper division CS data science courses. I guess first of all, thank you all of you who've emailed me telling me about how the constraints would affect your ability to complete the majors or the sequences. I've passed all that information on to a couple of people, to the head of the data science program itself, Professor Mark Huber, and then the chair of the math department and the dean of the college, and they're all working together on a plan to be able to ensure that the data mining course gets offered. So at this point, it's 100% sure that it's going to be offered either in the fall or the spring, but it's not yet sure exactly the time that it would be offered or who's going to offer it. So no need to worry about requirements. It will happen, we just don't know exactly how yet. Other announcement is that so last time we were talking about binary search trees, and we didn't quite finish everything that I wanted to talk about the binary search tree. So because of that, I extended the due date until Wednesday of this week, so you still have time to work on the assignments. And again, if you're working with somebody else or came to the lab session, then you have until Friday for the assignment. What we'll do for the first part of this class, just a couple of minutes, is look a little bit over some of the more code issues, give you a couple more hints on the assignment, and then we'll start on new material for today. I also want to highlight that I've added, and this was a couple of days ago, this was during the lab period that I did this, more hints to the assignment and some more starter code. So if you haven't, or I guess if you already, say previous to 4 days ago, pulled the changes to the repo and haven't redone the pull to update the code again, you're not required to, but you might appreciate having the extra starter code. Okay, so I'm gonna switch over to my terminal window right here. And the main thing that I wanna look at that we didn't have a chance to look at yet is the test cases for the BST. So I'm gonna go ahead and open that up in Vim. And again, notice that I did not CD into the tests folder. Instead, I put the entire relative path to the file that I want to open right here after Vim. You notice that for the past few class sessions, maybe a couple weeks now, I've been really trying to emphasize this, that you CD into the root of your project, and then you never touch the CD command again. Anytime you're opening a file or running a file, you always pass the full relative path to it, and that will ensure that you don't run into any errors. So let's open this up in Vim. And there's two things that I want to highlight. The first is how this is about this first set of test cases, this BST satisfied set of test cases. And what I want to highlight about this is that these test cases provide a good sort of variable for you to work with when you're working on your implementations and debugging them. And in particular, if we scroll down here, we want to find one of these BST variables that is in fact BST satisfied. So something like this one here, but let's get a slightly bigger one like this one here. So all of this code right here represents a binary search tree that's a valid binary search tree. And so this would be a great binary search tree to work with as you're debugging for your homework assignment. An easy way to do this, so in my Vim window right here, I'm going to open up a new tab. :tab E opens up a new tab. And what I want to open up is my bst.py file. So I did :tab E container/bst.py. And I notice up at the top, I have the two tab windows open. I've done this before, and I can press GT to switch between them. GT to switch between them while I'm in normal mode. And this, what I'm going to do is with my mouse or with my keyboard, I'm going to copy all of this. So in Vim terminology, I would say I'm going to yank these lines of code. And in order to do that, I'll press Shift V to go into visual line mode, and then use the up arrow to move up like this, and then the Y key for yank. You can see at the bottom left, it says 8 lines yanked. Yanking, again, is Vim's terminology for copying. And I'm doing this because I want to copy it from this tab, the test_bst.py file, into my bst.py file. So press GT to switch tabs over here. And now I'm going to place this new code at the very bottom of the screen. In order to go to the very bottom of my file, it's Shift G, capital G, takes me to the last line in the file. And then in order to paste the thing that I've yanked, I press P, and it pastes it down here. The indentation now is a little bit off. It's indented over to the right. I want to indent it back to the left. So what I'll do is I'll highlight the whole thing again, Shift V, and now I'm in visual line mode again instead of normal mode. You can tell that because on the bottom left, it says visual line mode down here. And now I could use the down arrows to go all the way down and highlight things. But instead, I know that I need to go to the last line of the file. So I'll press Shift G again to move me to the last line of the file. So it saved me a couple keystrokes there. And in Vim, the way you can indent a whole block of text at once is once you have it selected in the visual line mode, you press the Shift and then the less than sign. The less than sign, the way to think of it is it's like an arrow pointing your code to the left. And so it shoots your code one tab to the left. If you want it to indent to the right, the Shift greater than sign, shooting your code over to the right, shooting it over to the left. And now I have this BST variable that when I open up Python, I can actually just call this BST variable and run my inserts and all of my different functions on it for debugging purposes. In terms of the order that you want to implement these functions, the most important function to get correct. So what I'm going to do here is I'm going to press GG to send my code to the top. So GG takes you to the first line, 2 lowercase g's. Shift G takes you to the bottom line, GG to the top. And it's line 40, this is BST satisfied. I'm going to send my cursor to line 40 by typing 40, the number 40, and then GG. When you have GG by itself, it takes you to the top of the file. When you type in a number first and then GG, it takes you to that line. And I'm going to center my cursor on this line with ZZ. So it's real easy for me to jump around the file this way. And this is the first sort of big picture function that you want to get satisfied, get implemented, because all the test cases are going to really depend on this function right here. And in general, anytime you're implementing a new data structure, the first thing that you always want to do is have some sort of check to satisfy that whatever the properties of your data structure are, that you satisfy those properties. And so I already gave you this code for this part of the SBST satisfied, but it calls the underscore, the helper version of the function down here. And so that's the real one that you want to focus on. Here, I gave you some more starter code. This is an incorrect version of the code, though. This will not pass the test cases as is. And this has the common mistake that I was talking about in class last time of comparing the value of your node just to the value of your children. And you don't want to compare it to the value of your children. You want to compare it to the smallest thing or the largest thing in your subtree. If it's the left subtree, you want the largest value in the left subtree, or if it's the right subtree, you want the smallest value in the right subtree. So in order to get this implemented, you'll have to change these conditions here so that you're using the smallest and the largest values. That means you'll also have to implement the function for smallest and largest values. Do a quick search of this, /smallest, takes us to these codes down here. Sorry, this code down here. One of the things that, so So I can tell a beginner programmer from a not beginner programmer through a lot of ways. Just talking to people, one of the ways that I can tell that is that if somebody says code plural, so like I just did on accident, I said these codes. These codes refers to these passwords. It does not refer to multiple lines of text that is in a programming file. A lot of beginner programmers that haven't been around, especially non-native English speakers that haven't been around a lot of professional programmers, will refer to a file that contains many lines of code as codes, plural. But code, when it's referring to something that you're programming, is always a singular noun. And so that's just one of these sort of shibboleth sort of words that you can use to determine how experienced a programmer is. And so make sure that you're always using the word code singular instead of plural. Yes, so that was a short digression. I've implemented this find smallest function for you, and the find largest you can implement yourself following this same pattern here. So that's the first place to get started with this class, and then from there, my recommendation is doing the find, then the insert, then the remove. Inside of the test cases, so these test cases up here are sort of like the test cases that we've seen a lot before, where I just have one specific example and then am asserting one particular fact about the example. But then all of the other test cases are what we call property-based test cases. And we've seen this before in the sorting homework, but it's been a little while. And so we just wanted to highlight this again. But for each one of these test cases, what's happening is I'm using this hypothesis library, which is sort of an extension to the PyTest library. The hypothesis library gives me this decorator right here. Anything in Python that starts with an @ sign is called a decorator. And these are special types of functions that we'll talk in more detail about later how you create them yourself. But what this is saying is that the hypothesis library is going to randomly generate thousands of different lists of integers and pass them to this insert function. And your code has to be able to satisfy this, not just for a single list, but for all possible lists, all thousands of randomly generated lists that this library is going to generate. And so what it's going to do is it tests some property about your code. And one of the things that we mentioned before is that your insert function, if you've done it correctly and you have a valid binary search tree, then when you do your toList, you're going to get back everything that you've inserted. So this just ensures that you've gotten back everything that you've inserted. And it's also going to be in a sorted order when you do an in-order traversal like this. And then your BST satisfied should stay satisfied no matter how many times you call this insert function. There's quite a few test cases that test different properties like this. And again, each one of these, it's not just a single value that you have to get it to work with. You have to get it to work with all possible values of random strings, random lists full of integers that will get passed in. Does anybody have any questions on the BST assignment? Okay. So today and this week, we're going to start talking about something called an Avl tree. And this is the this is sort of like the big coolest thing in the data structures class. The implementation of it is one of the harder things in the data structures class. But what it does, this is the thing that guarantees us the log time search on everything. This is the thing that that Google is using every time you perform your search queries. It's using this cool data structure, something very, very similar to it, to get the good performance. So at the top of this file, the two pictures that I have here, this first one is well, these two pictures are about binary trees in general. And this first picture is from a math textbook where they're making fun of computer scientists. If you read the note down here, it's talking about the trees. The convention is that they grow upside down from the top to the bottom. And the conventional wisdom is that computer scientists did this because they've never been outside of their room, and so they never saw a real tree before. And so a bunch of computer scientists saw this math textbook and this joke, and so they decided to actually plant an upside down tree in order to prove that they have in fact been outside. So if you're wondering why all the trees that we've been drawing are upside down, it's modeled after this tree right here. And we'll be drawing a lot of upside down trees today with our discussing the Avl tree. Okay, so we've talked now about the binary search tree and the different algorithms that you can do on them. And I said that they're like, the goal of these algorithms is to be fast, but we haven't really formally talked about that too much yet. And so that's what we're going to start our discussion with today. The idea is that the binary search tree, the BST, is usually a good data structure, but it can sometimes become unbalanced, resulting in poor performance. And so I'm going to switch screens here for a second to draw some pictures, and then we'll come back and talk about these like formal theorems and corollaries. So I've switched screens over here. And what I want us to do is to have an intuitive definition of what this word balanced is supposed to mean. So intuitive definition of balanced. This word balanced comes up a lot in the computer science literature, and it has a lot of different formal definitions. Later on today, we'll see one of those formal definitions, but they're all sort of related back to this intuition that we're going to talk about right now. And so I'm going to draw two trees, and the first tree will be a balanced tree. I think last time I used a lot of numbers in my trees, and so this time I'm just going to use letters as my tree nodes. And in general, for any of these trees, you can use anything that you can compare with less than or greater than. And so I'm just using letters this time to help illustrate that difference. It doesn't have to be numbers, it doesn't have to be letters. It can be anything that's less than or greater than other things. So here, A, H, and S, and N, and Z. Here's an example tree that satisfies the binary search tree property. Every left child is less than, and in particular, not just the left child, but every left subtree. Every node in the left subtree is less than, and every node in the right subtree is greater than. So the greatest node in this left subtree is less than M over here. This H is less than M. And we say that this tree is balanced because, well, informally, every node has either either 0 or 2 children. This is our informal, intuitive definition of balanced. The more nodes have 0 or 2 children, the more balanced they are. And then the more nodes have 1 children, the less balanced they are. So this is a very balanced binary search tree. And now let's see an example of a very unbalanced binary search tree. We have A, then F, then H, then M, then N, then S, then Z, like this, all just in a straight line where they're all right children of their parents. And here, many nodes have only 1 child, and so it's unbalanced. The problem with the unbalanced tree is that, let's imagine we do a binary search for Z. If we do a binary search for Z, then we have to visit every single one of these nodes right here. But if on this tree over here we do a binary search for Z, then we have to visit very few nodes that we can cut off at each node. We can cut off a big portion of stuff on both the left and the right. And so another sort of slightly better definition of a balanced tree actually a much better definition of a balanced tree is a balanced tree has height that's approximately O of log n, whereas an unbalanced tree has height, so just approximately n, like this. The fact that over here we have so many children that are branching off both the left and the right subtrees of each of these nodes is what gives us this, this sort of log n factor of the height. And the fact that over here, we're only ever branching off one side, that's what gives us this kind of linear factor of the height. And so when people talk about like why they like balanced trees versus unbalanced trees, this is the good property of a balanced tree. And so on the left, the good property of a balanced, and then on the right, the bad property of an unbalanced. This is good. This is bad. Are there any questions about the intuition between a balanced versus an unbalanced tree? Okay. So the important thing at this point is that both of these are valid binary search trees. We would hope that our balanced binaries we hope that our binary search trees are balanced and not unbalanced, but at this point we don't have any mechanism for forcing them to be balanced. I'm going to switch back over to the notes now. And there's these kind of formal-ish theorems about our algorithms. The first theorem that we have is that the runtime of any operation, whether it's a find or an insert or delete operation, is O of whatever the height of the tree is. This is in the book, in the chapter on binary search trees. They go through and do this fairly formally, but for our purposes, it's enough to just have an informal intuition about why that's the case. And the idea is that if you're doing a find operation, well, you have to, in the worst case scenario, you have to visit every node between the root and whatever it is that you're looking for. And in the worst case scenario, whatever you're looking for is going to be a leaf that's far away from the root. On a balanced tree, because the height is bounded by O of log n, then that's what our runtime is going to be, maximum O of log n nodes that we have to visit. But in an unbalanced tree, linear height, we have to, if we're searching for Z, we have to visit all of these nodes, never get to prune anything, and so we have the bad runtime. So that's our property, that we can only guarantee that the height of a BST is O of n. And this is a very formal and correct use of the big O notation right here. Again, one of the common misconceptions that people have about big O notation is that it's only applicable for runtimes, but that's not true. Big O notation, big omega notation, big theta notation, they're all applicable for any function. Here, the function we're measuring is not the runtime of an operation, it's the height of a tree. and we've provided an upper bound on that height as O of n. And again, the O is intuitively like an upper bound, like a less than or equal to. A lot of people have the mistaken assumption that when you see O of n, that bound must be tight, but that's not the case. That the height of a binary search tree, we've seen that it doesn't have to be O of n. The height in this case is log n. And actually, so what our height satisfies, to really be formal about this, is our height on any BST, the height of any binary tree is omega of log n. So it's lower bounded by log n. It's impossible to have a tree has a shorter height than this, and it's upper bounded by O of n. And so we can't say anything about theta of the height, because these two things, we can't make the omega bigger and we can't make the O smaller. So they don't match. And then, so our corollary, combining that theorem and this property, is that the runtime of all these operations is going to be linear, O of n. And so now our goal, we're going to introduce this idea of a self-balancing binary search tree. And this self-balancing binary search tree is going to add new invariants besides the binary search tree invariant. That's going to somehow force that the height stays in this good regime, this log n regime. And so by guaranteeing that our height is logarithmic, we'll guarantee that our runtime is logarithmic by this theorem here. There are many different types of self-balancing binary search trees. We're going to look at the Avl tree. The Avl tree is my favorite of these self-balancing binary search trees for a number of reasons. And this is actually why I chose the textbook for this class, because I think they have a really clear explanation of the Avl tree inside of it. So one reason why I like the Avl tree is that it was invented first out of all of the self-balancing binary search trees, invented in 1962 by these two Soviet scientists. What the Avl stands for, it's just the initials of their names. And another reason that I like it is it's just much simpler than the alternative options. So there's a lot of different of these binary search trees that are self-balancing. And yeah, Wikipedia has great articles on all of these if you're interested in them. All of these trees here were invented at least a decade after this one here. The red-black tree is the next one that was invented after the Avl tree. And this one was invented by a West German researcher, Rudolf Bayer. And so the West here is important because at the time, Germany was still split into East and West Germany. And I believe that this is the first instance that the non-Soviet bloc world learned about self-balancing binary search trees. So the Soviets invented it originally, and they had this technology for almost a decade before the Western world caught up. The red-black tree is also a very popular tree to be taught in like intro data structures courses as the first self-balancing binary search tree that you learn. Let's see, most data structures courses just pick one, either the red-black tree or the Avl tree, and that's the one that you learn. The actual operations for how to do things are very different, the implementations, but the end result for both of them is that you get a tree, a binary search tree that's bounded in height by log n, and so you get the good runtimes. Yeah, so the red-black tree is, I think, significantly more complicated than the Avl tree. And my impression about the only reason why people teach this one over the Avl tree, at least in the the English-speaking world is because of, for a long time, nobody knew about the Avl tree because it was a Soviet thing. And then after people learned about it, they just wanted to keep using Western inventions and not this Soviet invention. Okay, so all of these data structures somehow add a new invariant on top of the binary search tree invariant that enforces that the tree will remain balanced. And the Avl tree uses this invariant right here. We have what's called the balance factor of a tree. And this is going to be our formal definition of what it means for a tree to be balanced. We say a tree is balanced if the balance factor, so this formula right here, is either -1, 0, or 1 for every node in the tree. If it satisfies that, we say the tree is balanced. If it does not satisfy that, we say the tree is not balanced. In the balance factor, what it's equal to is the height of the left subtree minus the height of the right subtree. If you read the Wikipedia article about the Avl tree, they reverse this, the definition of the balance factor, say the height of the right subtree minus the height of the left subtree. This is the way that the convention that the book uses. And every textbook and web page that's talking about the Avl tree uses one of those two conventions, and you always have to just figure out which one they're talking about and sort of mentally adjust yourself based on that. What we'll end up seeing is that every tree, every binary search tree that satisfies the Avl invariant is going to have height that's upper bounded by O of log n. We saw that every search tree is also lower bounded by omega of log n, so that'll mean that the height is theta of log n, and so all of our runtimes will be theta log n as well. Let's go now back to our drawing sketch area, and we'll see a bunch of examples of this balance factor and get a little bit more intuition for it. So here we go. And we'll come down, let's see, let's actually come up here. And we're gonna calculate the balance factor of all of the nodes in these two trees right here. So we'll start with the left-hand side. And on the leaves have no children on either the left or the right. So the height of the left subtree and the height of the right subtree are both 0. And so the balance factor of a leaf is guaranteed to be 0. I'm going to write the balance factor in orange next to each node, like this. So it's all zeros. And then our F and S, well, the F has a left height of 1, a right height of 1, and so 1 minus 1 is 0, and so the balance factor is 0. Similarly for S. And the M, the height of this tree is 2, the height of this tree is 2, 2 minus 2 is 0, so again 0. So because all of these balance factors are 0, that's like the best case scenario for being balanced, and this is an example of a valid Avl tree because every node has either 0 or 1. Over here on the right, we calculate the balance factors. The balance factor of the Z here is 0. And then we do the left minus the right for this S, and the left is 0, the right is 1, so the balance factor is -1. Here in left of 0, right of 2, -2, and then so on, -3, -4, -5, -6. All of these numbers are very far away from 0, and so that gives us a measure of just how unbalanced this tree is. Because the balance factors are far from 0, it is highly unbalanced. It's also not a valid Avl tree because the numbers are not contained in -1, 0, or 1. So both of these two trees are somehow a little bit too extreme, maybe, to be super interesting. So I'm going to draw 2 more example trees right here. And I'm going to I'll calculate the balance factor for all the nodes here in a minute, but first I want you to I'll give you a minute to try to calculate the balance factors yourself. So I'll draw these nodes, draw these trees. We have A, and then F, N, H, S, Z, like that, and then A, F, S, Z, M, H, and N, like that. And so spend a minute for both of these two trees and try to calculate the balance factor of each node. And then in a minute, I'll come back and do it up here. So now would be a good time if anybody has any questions, a good time to ask questions.
Hey, Mike. Just very quickly, I know we will probably go over this, but I'm just having a little bit of trouble trying to understand where to start.
Sure. So the place to start is with this formula right here. It's the balance factor is the height of the left subtree minus the height of the right subtree. So for each one of these nodes, calculate what is the height of the left subtree and the height of the right subtree, and do that formula. So here for the A, the left subtree, there is none, so it has height 0. The right subtree, also 0. So 0 minus 0, we get 0 for A. If we were to look at, say, this F right here, the height of the left subtree is 1. It has 1 below it. The height of the right subtree is 2. And so we do 1 minus 2 and get -1.
I see.
For that F.
Got it. Thank you.
Mm-hmm. So I'll go ahead and keep working on this left tree over here. This H, nothing on either side, 0 and 0. We get a 0. F has 1 and 1, so 1 minus 1 gives me 0. The Z over here is a 0. This S has nothing to the left, 1 to the right, 0 minus 1 is -1. And this N has 2 on the left and 2 on the right, so 0 minus 0, or sorry, 2 minus 2 is 0 and 0. One of the key things to keep in mind is that we're not counting the total number of nodes on the left and right. So the number of nodes on the left here is 3, the number of nodes on the right is 2. Instead, we're counting the number of levels, the height. So there's 3 nodes, but there's 2 levels, height 2. And 2 nodes, 2 levels, height 2. So 2 minus 2 is 0 for N. Over here, this A, 0, leaf nodes are always 0. Anything that has the same on both sides is going to be 0 as well. And then this S is the most interesting one, that on the left, we have 3, 1, 2, 3 levels. And then on the right, we have 1. So we have 3 minus 1 gives us 2 for the balance factor right here. So the rule for an Avl tree was that the balance factor, again, I'll write BF for balance factor kind of throughout the notes, is contained in -1, 0, or 1 for an Avl tree. So on the left-hand side, we are in fact an AVL tree. Everything is contained within. It's either 0, -1, or 1. So this is yes, an AVL tree. Here we have this node up here, this 2. So this is not an AVL tree. Are there any questions about how I calculated any of these numbers or why this one's an AVL and this one's not an AVL?
I have a question about the not AVL tree.
Mm-hmm.
It's only not AVL because of the S node, correct?
Exactly. So
Okay.
all it takes is one node for it to become not an AVL tree. If we were to add more data to this tree, say by doing something like, so I'll first redraw the tree exactly as it is. S, F, A, M, H, N, Z, and then add, say, a T coming off over here. And then when I added this extra level right here, that would change the balance factor of both the Z node right here becoming a 1, left of 1 minus 0, right is 1. And then it would change the balance factor of the S, 3 on the left, 2 on the right, to 1 as well. So this one is an AVL tree. Understanding these balance factor sort of computations is going to be really crucial to understanding sort of the rest of our entire discussion about the AVL tree. Nothing will make sense if you don't understand the where these numbers are coming from. So if you have any more questions about it, now's a good time to ask.
Mike, I had a quick question. Can you have a balanced binary tree that's not an AVL tree?
This is a fantastic question. So so our condition right here about this balance factor, sort of the purpose of it is to enforce somehow that the tree is going to be balanced. And it'll, in particular, enforce that the height will be log n. There are other rules that we could have that would also enforce that the height is going to be log n. And those rules may or may not satisfy this rule as well. So for the red-black tree, for example, the other one that's commonly taught, red-black tree, every red-black tree is balanced in the sense that the height is O of log n. But it's also the case that not every red-black tree is an AVL tree, and not every AVL tree is a red-black tree. So if your definition of balanced is coming from the red-black tree definition of balanced, that invariant, then yes, not every AVL tree will satisfy that. And not every tree that has a log n height is guaranteed to be an AVL tree. So this one, it appears an example of one that this is kind of pretty balanced. There's only just really one node that's off by 1. And so I'd be pretty happy with doing binary search on a tree that looked like this. But it's not technically an AVL tree. Good question. Any other questions so far? Okay. So what we're going to do next is we're going to revisit just the standard binary search tree insertion. algorithm. So Bst Insertion. And we'll have the following list of numbers that we're going to insert. E, C, F, B, D, A. I guess list of letters, not list of numbers. And if we insert these things one at a time, then the resulting tree that we'll get is, so starting with E, here's our E. The balance factor right now is 0, so it's a valid AVL tree. And then the next thing we have is a C, starting at E, going to the left. We have a C here. Balance factor of the E is 1, balance factor of the C is 0, so this is still a valid AVL tree. And so far, doing the normal binary search tree insertion has given us a valid AVL tree. We do the F comes off to the right over here. Now everything has a balance factor of 0, so we're good still. To insert the B, start at E, go left. Now we're at C, go left. Add the B right here. We're still a valid AVL tree that B, F both have a balance factor of 0. C has a balance factor of 1, 1 to the left, 0 to the right. So balance factor of 1. E has a balance factor of 1, 2 to the left, 1 to the right. 2 minus 1 is 1. And so everything is still balanced. We're still good. Let's add the D. Comes over here. Everything stays valid binary search tree. And now let's add this, this A. The A comes down over here. So we, most of the time when doing a, now that we've added this A, let's go ahead and annotate this tree with all of the balance factors. So all of the leaves get 0s. This B is a 1, 1 to the left, 0 to the right. 1 minus 0 is 1. This C is also a 1, 2 to the left, 1 to the right. 2 minus 1 is 1. But now this E has 3 to the left, 1 to the right. 3 minus 1 is 2. So this is no longer a valid AVL tree. Most of the insertions maintained balance. By which I mean maintained the AVL property. It's only occasionally that the property gets violated. And when it does get violated, one of the properties that we have is that, scroll down a little bit more. Oops. Each insert can change the balance factor of any other node by, at most, plus or minus 1. So this is one of the key concepts right here of how, this is how quickly the balance factor can change, or what are the things that can cause the balance factor to change. And so if we think back to before we had inserted the A, then our tree looked like E, C, B, F, D like that. And balance factors 0, 0, 0, 0, 1. So this is what the tree looked like before we inserted the A. Up above is after the inserting of the A. And when we inserted the A, so when we added the A right down here, then the balance factor of each of these ancestor nodes changed by 1. Went from 0 to a 1, 0 to a 1, and then 1 to a 2. And because when we add just a single node at a time, the most we can change the height is just 1. You can't change the height by 2 by adding just a single node. So that's why the balance factor of all of these nodes can change by at most 1. And when a node changes its balance factor, the only nodes that can possibly change a balance factor are the nodes that sit between the node that you added and the root. So because I added the A down here, that can't change any of the sub-children of F, even if F had some big trees that were coming off of it. By changing something way over here, that can't affect the balance factor of F because it doesn't affect the height of any of its subtrees. The only subtrees that are affected are the ones that are in this path between the node that we added and the root. So each insert can change the balance factor by at most plus or minus 1. And it's only the ancestor nodes of the new node that change. Oops. These are the sort of the two key facts that we'll use to design our AVL tree insertion algorithm. And our idea is going to be that we'll first just do the insertion like normal for a binary search tree. Most of the time, we're not even going to have to do anything additional beyond that. Most of the time, our balance factors will stay good, stay in the 0, 1, -1 range, and things will stay balanced. But if things become unbalanced, the only possible ways they can become unbalanced are this path right here changing by plus or minus 1. That means that the only unbalanced values that we can have are these 2s or -2s. At the bottom down here. Bad values are plus or minus 2. And so what we need is some sort of procedure that's going to take a node that's at plus or minus 2 and convert it back into the valid range for a for an AVL tree. So what we need, procedure that takes a node with balance factor plus or minus 2 and converts it into an equivalent BST and we'll see exactly what we mean by equivalent here in a little bit. But an equivalent BST, so containing the same nodes inside of it with balance factor -1, 0, or 1. If we had some sort of procedure that could do this, Then after doing our insertion, we would just apply this procedure to any nodes in this chain that the balance factor has changed to be either 2 or -2. The procedure for doing this is called a rotation. And we'll talk about exactly what those look like next. Before we talk about the details about what a rotation looks like though, it'll be helpful if the motivation for why we want this rotation is clear in your mind. So are there any questions about why, what we need right here, or why it's the only sort of bad conditions are the 2 or -2 balance factors? Okay. So now we'll look at what this procedure actually is. And there are 2 forms of rotations, a left rotation and a right rotation. So we'll start with the left. In a left rotation, basically what we're going to do here is we're going to just show some examples to get you the intuition behind what these rotations are doing. And we'll start with the simplest possible example of a basic tree that contains 3 nodes like this. In this tree, it's not a valid AVL tree because balance factor of C is 0, B -1, A -2. So this is the node right here that we're trying to target, that we're trying to fix this node so that it doesn't have the -2 balance factor. And in a left rotation, or in any rotation, you pick 2 nodes that are adjacent to each other, a parent and a child. And in this case, we'll pick the A and the B. So this is a left rotation on A and B. And what we do is we make B the parent of A. So it'll look like this, B and A and C. These 2 trees right here are equivalent to each other because they contain the same nodes. They're also both valid binary search trees because they satisfy this BST property of smaller to the left, greater to the right. But now the one on the right, the tree on the right, is balanced. Everything has a balance factor of 0. And the one on the left is unbalanced because it had this, this -2. And this left rotation is fixing this, converting this tree right here into this tree right here. So this is a very simple example. This is the simplest possible example of the rotation. So next we'll look at the more general formula for this rotation. When we write out these general formulas, they're typically written out as follows. We'll do it like this. So we have a D node, and then this is going to be an F node right here. And I'm going to draw circles around these nodes. So I've been kind of neglecting drawing circles around all of my nodes previously, just under the understanding that they're all containing circles. And then I'm going to draw left and right children of these over here. Oops. So I need that to be a triangle instead of a circle. A triangle like this, and a triangle like this, and a triangle like this. And the name of this triangle will be A, the name of this triangle will be E, and the name of this triangle will be G. And my handwriting is very sloppy right now. That's a G inside of there. The reason I've drawn these as triangles is because they're intended to represent not just a single node, but an entire tree of nodes. And when we do the transformation on this left rotation between D and E here, then the E will come up to the top, still as a node. The D will become the left child of E. The
Mike,
left,
I think you mean to say F.
thank you, yes. Let me fix this right here. Yes, that is an F up here. We did the left rotation between F and D, F going to the top, D coming down below. The A stays as a left child of D. The G stays as a right child of F. And now the E right here switches from being a left child of F to being a right child of D. This is the part that takes a little bit of thinking about to justify to yourself that this is an okay thing to do. But if everything inside of E is greater than or equal to D, and we had that property already in this left tree over here, that the binary search tree property says that everything to the right of D must be greater than or equal to D itself. And so E over here is greater than or equal to D because it's to the right. And so we can attach it directly to the D without violating the binary search tree property. And so this is a DF left rotation. In the book, and if you look on Wikipedia, this is how the actual rotations will be defined, and it'll just be understood that it'll be assumed that you understand that a triangle means an entire subtree, the node that starts here plus all of its children, and that a circle represents a node itself. So let's do another example. We'll have D here, and F like this. And now instead of drawing the triangles, I'm going to draw actual tree, B, and A, and C, and E, and G, and H, say like that. And I'll do the same left rotation on DF. So I'm doing the rotation on this node and this node. And what that gives me is that the F will come up to the top. Everything that used to be a right child of F, so everything that was in this G triangle over here, will stay as a right child of F. So we have the G and the H like this. The D now becomes, it used to be the parent of F, now it becomes the left child of F, like this. And everything that used to be a left child of D stays as a left child of D. So both the root of that subtree and all of its children. So there's the B, A, C, like this. And the E used to be a left child of F, but whatever used to be a left child of F becomes a right child of D. And so the E comes over here like this. And so this is a more detailed example of a left rotation. But if you look in the book or any other source, they're never going to provide out a detailed example like this. It's always going to be with these triangles. And you have to understand that the triangle represents not just one node, but all the nodes that are children and descendants of that node as well. Are there any questions about just the mechanics of what this left rotation is supposed to do?
I have a question, or I guess just a clarification.
Sure.
So when we are performing a left rotation, we are always choosing the right child of the unbalanced node.
That's a good question. I think the question is fundamentally about like, so up here, what I've been trying to talk about is just the how of the rotation, but the question is like the when or the why of the rotation. And at this point, you shouldn't be thinking about like unbalanced versus balanced nodes. You should just be thinking, I've specifically given you two nodes and I'm telling you that they're rotating. And so why it's those two nodes that I picked, at this point, we don't know. We'll see that in some situations, the D will be the unbalanced one, and in some situations, the F will be the unbalanced one. But we're just gonna develop these two tools, and then we'll see there's 4 cases of when to apply them, and but we can't do that until we get the, just what are they doing down. That's a good question. And we'll probably not get to it today, but on Wednesday we will. Any other questions so far? Okay, so I want to talk about a property of this left rotation. So if we do a left rotation, between two nodes D and F, so D was the parent of F. Whenever we're talking about these rotations, the first one over here will be the parent of F. This is called a left rotation because the F is going to the left, going up. Well, when we talk about right rotations next, the difference is that a right rotation, if we did a right rotation between B and D, B would become the parent of D. But we'll see that here in a second. The left rotation on DF, the main property is that if the balance factor of D was -2, then the new balance factor must be 0, 1, or 2. And then again, when we talk about the why of when we're going to perform the balance factor rotation, we'll do the left rotation on this D node when it's -2, and the results will be either 0 or 1. But importantly, we can never get a situation where, say, the balance factor becomes 3 or becomes -3 by doing this procedure. So we're never going to get worse off in our balancing situation. On a right rotation, we'll real quickly describe what this is. So if you have A, B into C, like this, the right rotation of BC becomes A into B into C. So the B moves to the right, takes the place of C as the root of the tree, and C comes down to the right. The more fully formal definition is that if we added these the trees, so this is going to be circles, and then we have our A triangle, our E triangle, and then our G triangle like this. Oops. Then that's going to take us back to D, F, this with A and E and G. And so these diagrams are hopefully looking familiar to you, that this is the same pictures that we saw with the left rotation. They're just in the opposite order. And so a right rotation is the exact opposite. It just undoes the left rotation, and a left rotation would undo a right rotation. We have a similar property as this for the right rotation, that in a right rotation, if the previous balance factor of the root node, so in this case F, and in this case it's a positive 2, then the resulting balance factor of the new root node D is 0, -1, or -2. And so again, we can never make our situation worse. We can never make our tree more unbalanced by doing a right rotation. At worst, we just become unbalanced in the other direction. But we also have these two possibilities here of making it more balanced. So next time, what we'll do is we'll see how to combine these left and right rotations together into a system that's going to guarantee that you're always going to reduce your 2 or your -2 down into that -1, 0, 1 range, and that will guarantee that you satisfy the Avl tree property and have the good run times. Yeah, your homework's already posted, so you can take a look at that. But it's really won't be until Wednesday after we talk about putting these right and left rotations together that you'll actually be able to implement anything. So yeah, that's everything for today. I'll stick around. I have office hours now to answer questions about this or the binary search tree or anything else. And I will see you all on Wednesday.